Okay, everyone, this is a quick video for us to discuss the standard error of the mean. So this is where things get a little complex and it's difficult for me to explain this in writing or in an email. So I hope that this will help you guys to understand some of these concepts and the calculation. So I wanted to take a step back and look at why we would calculate the standard error of the mean, kind of theoretically, what is the purpose of this? So if we think about the difference between a sample and a population, so typically what we're interested in research is the population as a whole. But all we have access to is a much smaller subset of that population called a sample. So we have to understand and accept that the data that we are acquiring from a sample is limited and potentially or almost certainly flawed in some way. So if we look at what's called the central limit theorem, it introduces some important concepts and properties. So the idea is that if we have a population such as the one that we have here, so you see that we have a population of 1 million people, and if hypothetically we knew facts about the population, which very often we don't, but let's say for these purposes, theoretically, we know that at the population level, the mean of our variable is 50. So we could say maybe this is some variable that measures IQ or anxiety or creativity or whatever it may be. The mean of our variable at the population level is 50. Now, if we collect repeated random samples from this population, these random samples are only going to approximate these population parameters. So it's only going to approximate the population mean. So let's say that we collect from this 1 million people, this population, we collect a sample of 100 participants and we administer our scale or test or inventory, and we calculate the sample mean for my variable of, let's say, anxiety. This sample of 100 people, if I drew it from the population and calculated the mean, say that the sample mean that I calculate is 55. So here we're overestimating the population mean. So our sample mean is a little bit higher. We may draw another random sample of 100 people from the population, again administer our test, and find that this time the average anxiety score for our sample is 50. So this time we got it right on. So that's excellent. But maybe we do it again, we draw another 100, and this time it's underestimated and we get 47. We may draw another sample of 100 people, and this time our sample mean is 42. Another one, and our sample mean is 60. So the idea is that we have, despite the best attempts to collect a truly representative or random sample, we're still going to have to accept some level of random error. So this doesn't necessarily mean that our methods for data collection are flawed in this particular study. Every researcher should expect some type of random error. So the idea is kind of sometimes easier to understand if you think about you as an individual taking repeated tests, a repeated IQ test, for instance. On some occasions, the score that you get may overestimate your actual IQ level. Maybe you're having a really good day, you had that extra cup of coffee, maybe some of the questions you guessed and you just got lucky, right, and got them correct, and so your score is inflated. It's an overestimation of your true underlying IQ. Now, on other days, you may be having a bad day. You didn't drink your cup of coffee, you didn't get enough sleep the night before, you made some guesses and they all went wrong. Right? And so now we have an underestimation. Maybe you made some mistakes and bubbling in your responses, and so your score is actually lower on the test than what your actual IQ is. So the theory of the central limit theorem here, the idea is that the best estimate of the population parameters is, if we don't know the population parameters, the best estimate would be the average of a very large number or an infinite number of random samples drawn from that population. So even though each individual sample statistic may be a little off, maybe an overestimation or an underestimation, if we average all of these together, what we should get, if we draw infinite numbers of random samples from the population, we average all of those sample statistics together, what we should get is the population value. And you can see if you took these values here, so if we take 55 plus 47 plus 50 plus 60 plus 42, we get a total of 254 if we divide that by 1, 2, 3, 4, 5, our 5 samples. What we get here out of these is an average of 50.8, which is really close to our population statistic, right? Our population mean. All right, so that's important to understand because typically what we do is we just collect one sample. We're not collecting, as researchers, an infinite number of samples or even a very large number of samples. We may collect 1 or 2 samples and calculate the sample statistics and use those as an estimate of that mean value, or sorry, that population mean value. So this is where the standard error of the mean comes in, because we're recognizing that there is some error in the process. Even if we conduct the best study ever, there's still going to be random error that we have to account for. So this is what we're measuring. This is what we're getting at with the standard error of the mean. So what this will give you is an approximation of how much error to expect. And you hear this a lot, say with political polling. For instance, they may say that this candidate is expected to win or expected to get this percentage of votes with a margin of error, right? And so that's kind of what we're generating here, that margin of error, or what we're going to call the standard error of the mean, right? If we're estimating the mean from our sample. So the first thing that we have to ask is, do you have the population standard deviation? Are you given the population standard deviation? Or instead, are you calculating the standard deviation from the sample, right? Are you using the sample to estimate the standard deviation? Now, in practice, it's not very likely or typical that we would know the standard deviation of the population, but we're using this kind of more as a stepping stone to help you better understand the calculations. And so let's say that we do have the population standard deviation. And I believe for most of your homework questions, maybe all of them, you are given the population standard deviation. But on your quiz, you will have a question in which you're specifically told this is a sample standard deviation. You're using a sample to estimate the standard deviation. And so that formula and those calculations will be a little different. But let's start out with a scenario in which we collect data for 200 participants. We have 200 participants in our sample, and we calculate and get let's keep our mean of 50. And if I tell you that the population standard deviation is equal to, let's say, 8. Here, I would ask you to calculate the standard error of the mean given this population standard deviation. And what you'll use is our N, or our 200 participants. So let me actually go here and get, sorry, I want to be able to draw. Oh, okay. So what we would do to calculate the population standard error of the mean is that I would take my population standard deviation of 8 and I would divide that by the square root of 200. So the square root of my N, my total number of participants, which is 200. So the standard error of the mean in this particular example would be, let's see, we would take our 8 divided by the square root of 200 to give us 0.57. So the standard error of the mean here is 0.57. Now, let's say that we had a very similar situation in which we're told that, again, we collect data on 200 participants and we calculate a mean of 50. We also calculate from the sample data a standard deviation, so a sample standard deviation of 8. So this time, we are using sample data here. We're estimating our mean. We're also estimating the standard deviation. So now, the formula for our standard error of the mean is just a little bit different. So we would take the same standard deviation. This time it's our sample standard deviation of 8 divided by the square root of 200, our N, minus 1. So our formula would actually be, our calculation would actually be 8 divided by the square root of 199. Now, I know it seems kind of like these statisticians are just trying to trick you. The idea behind subtracting 1 from the N is that we are using the sample data to estimate two different things. So our estimation of the standard deviation, given our sample data, is partially dependent upon this estimation of our mean. So we're attempting to estimate something from an estimation. And so we have to account for that in our equation. We don't know the population standard deviation. We need to account for that in our formula. So we're subtracting 1 from our total N. And so it shouldn't change it much, but let's take 8 divided by the square root of 199. And this time we get, that our value is 0.57. So within rounding, it's the same, but as our sample size decreases, if we had a much smaller sample size, then the fact that we're subtracting 1 from our sample size is going to matter a lot more. So the difference between 200 and 199 is not as great as, say, the difference between 10 and 9, for instance. All right, so I will post another video in which we walk through the calculation of confidence intervals and kind of why confidence intervals are important and how we could use them.